Thanks for the introduction. So yeah, I'm going to talk about the effect of a screening mechanism on black hole binary inspiral waveforms. So in short, it means that I will show you here in this presentation the work we've done, where our goal was to find the effect of a scalar field on gravitational wave when this field is screened close to the source of the scalar field of the gravitational wave. And so in this presentation, I will first introduce to you what is scalar tensor theories, what is a screening mechanism, and then I will go and show how to find gravitational wave, or like to calculate gravitational wave in general relativity. So I'll go back to the background a bit, and then we will add the scalar field and calculate the effect of the scalar field on those gravitational waves that we would have calculated for general relativity. So first, why do we study scalar tensor theories? So there are different reasons, more or less convincing. The one that is usually cited the most is that the cosmological constant is very small, and you need a very strong fine-tuning to satisfy observation. And this is usually unsatisfactory for physicists because we would like to predict this behavior. A second reason connected to the first one is that there is a failure of quantum field theory to describe accelerated expansion using vacuum energy. So you can calculate the effect of vacuum energy on space-time, and it would behave as a cosmological constant, but this one would be too large. And also, if you do the renormalization and decrease the effect of this cosmological constant using counter terms, if you do the two-loop calculations, you would find that the two-loop correction would spoil the counter term of the first loop, and so you cannot actually have any prediction from quantum field theory on this vacuum energy effect on space-time, and so you would need the UV complete theory to calculate this, and this is unsatisfactory as well. Another thing why we would study scalar tensor theory is that string theory is thought to be incompatible with de Sitter space, so with the positive cosmological constant. And so it would be helpful for a theory like this to have a scalar to explain the accelerated expansion. And also we have a scalar field in string theory that are predicted. And so it makes sense to study scalar tensor theories for in the context of string theory. And finally, we can also imagine this scalar field to be the representation of the symmetry breaking of time translation. So if gravity at large scale does not preserve time translation symmetry, there would be a generated scalar field in the same way you have the Higgs boson. And this is in the context of the effective field theory of dark energy. So in a sense, studying scalar fields in cosmology is like testing the foundation of general relativity, and in particular, it's the symmetry of the time translation. So, okay, what do we mean exactly by scalar tensor theories? So the most general scalar tensor theory that has a second order equation of motion that is invariant under diffeomorphism and the Lorentz transformation are the Hondensky theories. And if on top of that, you restrict that you have luminal propagation of gravitational wave, you get this action. So yeah, it makes sense to assume that you have luminal propagation of gravitational wave because of the neutron star merger that put a very strong constraint on the speed of gravitational wave. So in this action, you see that you have a non-minimal coupling between the scalar field and gravity. Here we are in the Jordan frame, which means that the scalar field does not appear in the matter action. It only interacts with matter indirectly through the Ricci scalar. Then you have those functions G2 and G3 that are arbitrary and they depend on the scalar field. And X is the kinetic term of the scalar field. So we'll have 1/2 d phi squared. And here you have the D'Alembert operator of the scalar field. Because of solar system constraint and pulsar timing, mostly, we need to recover a general relativity at short scale or in high density region. Otherwise, your theory will be incompatible with observation. So you want your theory to modify cosmology, but does not modify the solar system experiment. And for this, theories that are used nowadays have what is called a screening mechanism. and they can come in different and various forms. You have the chameleon screening and the camouflage screening that has where those function needs to take a certain form, and you have secondarity screening like the Weinstein screening. And what those screening mechanism does is really that they reduce the dynamical part of the scalar field at short scale. So we can imagine it a bit under this form schematically. So you have a source, either the solar system, black holes, or pulsars, that is either massive or in a high density region. And because of the screening mechanism, the scalar field really does not behave much. It's really dynamically just a constant. And when you leave this screen region where the scalar field is screened, you have the scalar field can behave as it wants and is less constrained, so you can recover cosmological observations and things like that. So you can really imagine the screening mechanism as something behaving in this way. All right, and what about the screening mechanism in the context of gravitational wave? So up to now, it was assumed, since black holes are usually in high density region like galaxies, or they are themselves very massive, it was assumed that the source was not emitting any scalar wave, it was only emitting a gravitational wave. And once this gravitational wave was leaving the screened region, it could interact with this background scalar field that would generate this accelerated expansion. And this background scalar field can evolve in through cosmological between the observer and the source. And while the gravitational would travel to us, it would interact with this background field and modify the gravitational wave. In particular, in this work by Charlie and some of my colleagues, they've shown that it is not possible to observe a variation of the background field in the way. The only thing you can really measure is the value of the field at the position of the observer compared to the value of the field at the source. So it's very limited to test scalar tensor theories in this way. But as we saw, even though the scalar field that is emitted at the source is very small, it still exists. And furthermore, when it leaves the screen region, it might not be so small because it's unscreened anymore. So the question we were after with my colleagues is to know, can we actually assume that the scalar field emitted by the source can be completely neglected? We found that there are mainly three places where the scalar field can affect gravitational field. So while it's still in the screen region, the scalar field can still affect slightly the gravitational wave. Even if it's screen and small, it would still affect at the beginning the gravitational wave before it reaches the screen region. And also, because we have now a scalar field, it modifies the equation of motion for the source. So the source does not orbit in the same way, and the gravitational wave would be then influenced. And once both waves reaches the unscreened region, then the scalar wave is not screened anymore and might interact in a significant way with the gravitational wave while it's traveling to us. So my goal here is to present to you how do we calculate those three contributions from the scalar field. But first, let's start with general relativity. So to find the gravitational wave in general relativity, we use the Post-Internal formalism. So we start with the Einstein field equation, and we make a change of variable. Instead of taking the metric as being our main variable, we take this h mu nu that I call in this presentation the gravitational field. And if you make this change of variable, you find the wave equation, a wave equation. So you have the gravitational field. Here you have the D'Alembert operator on flat space. And here you have an effective stress energy tensor that depends on the matter content, the energy momentum tensor, and it depends on itself also, the gravitational field and its derivatives. So that's where the big difference comes with electromagnetism. While in electromagnetism, you don't have this effective stress energy tensor that depends on the field itself. So when the wave is generated and travel through empty space, the wave would not be modified. But in gravity, while the wave is traveling through cosmological distances, it would start to self-interact and be modified. So
So we need to take into account this self-interaction between the field and between itself. So to solve a wave equation, we use what is called retarded integrals. So you do the integral over all space-time, or no, sorry, all space of this effective stress energy tensor on a retarded time. So you take the time minus the relative position here, and you do the integral over all space. And that gives you the solution. So how it is done usually in general relativity, we separate it in two ways. We have the near zone that is close to the source, and the radiation zone where you're far away from the source. So you have really those two zones you integrate over, and we make different assumptions depending on the zone we are in. So schematically, it looks like this. So if you have a source, you're in the near zone, so close to the source, you have the energy momentum tensor that is non-zero because you have objects orbiting each other. And in this zone, we assume the gravitational field to be instantaneous. Because everything is closed, you assume that there is no retardation effect. And so the black holes, for example, in this case, they would affect each other immediately. And so we assume this gravitational field to be instantaneous. If we now make the integral, the retarded integral over the near zone, it would just give us a gravitational wave that would travel between the source and the observer. And this gravitational wave would not be affected by itself. Right? It would just travel through empty space and reaches us, and that's what we observe. But that's the difference with electromagnetism. So when the gravitational field is traveling through this radiation zone, it creates, if you want, an energy momentum tensor, and this energy momentum tensor would then itself create a gravitational wave. So you have, because there's a wave here, there's an extra wave that is generated. And now, if you do the integral over all the radiation zone, you get the full contribution from the radiation zone of this generated energy momentum tensor in the radiation zone. And to find the gravitational field in the radiation zone, you do an integral, a retarded integral over the near zone. So, but instead of evaluating this integral at the observer position, you evaluate the integral at an arbitrary position in the radiation zone. So mathematically, it looks like this. So let's start with the near zone. So we assume the energy momentum tensor for matter to be sum of point mass object. So in this case, two black holes. So we have M1, M2, U1 and U2 is the velocity of the two black holes. And here you have X1 and 2 is the position, the instantaneous position of the two black holes. To find the instantaneous gravitational field in the near zone, we use what is called the Post-Internal Approximation. We say that the gravitational field is small, and so we put it in the wave equation, and we solve it with retarded integrals. So on the left-hand side, you have the gravitational wave at first order, the gravitational field at first order. And on the right side, you also put the gravitational field at first order, but fortunately, in the effective stress energy tensor, this gravitational field only appears squared. So you only have h1 squared or the derivative of h1 squared. And so since you have first order but squared, it becomes higher order. And so it cancels. It does not contribute for the leading contribution of the gravitational field. So what we just need to do is to integrate this energy momentum tensor. And depending on the matter we have, you can just integrate this. So once you have the first order gravitational field, you can go to higher order, right? You plug in this and you keep only higher order terms of order 2. On the right-hand side, again, since it's squared, you don't have terms that are of order 2 on the right-hand side. You just have the remaining first order, and you can do again the integration. And you can do that as many times as you want, but usually we stop at the order 2. And you get what is called the post-Internal approximation of general relativity, where you describe each component of the gravitational field with different potential. Here, typically you have the Newtonian potential, where it's the integral over the density, and the other potential, like the derivative of x, p, u, I, pij, they're also potentials. I don't write their expression; it's not useful here. but they depend typically on the velocity of the two black holes, on the densities, on the acceleration sometimes. So it's really those potentials, they can be calculated using the matter content. So if we know which black holes we have, we can say, okay, so we can calculate the metric in the near zone. So now we know the energy momentum tensor and the metric in the near zone. So we can make the integral over the near zone. So we have the effective stress energy tensor. We plug in the energy momentum tensor and the near zone gravitational field. And we do this retarded integral. So now we consider the retardation effect, and we evaluate this the solution at the observer. So now in practice, calculating this integral is not straightforward, but we can make different assumptions. First, we can neglect terms that decay faster than 1 over r, where r is the distance between the observer and the source. That makes sense, because if something decays faster than 1 over r, it would be completely insignificant for our detectors. And then second, we can also use the conservation of the effective stress energy tensor to rewrite this integral in terms of sum of Epstein-Wagoner moment, if you want to take a look in the literature. And those moments are easier to calculate, and we can express then the solution in terms of those moments. Since we know how gravity behaves in the near zone, we can also find the gravitational field in the radiation zone. We do the same. We take the retarded integral over the near zone. And this time, instead of evaluating it at the observer position, we evaluate it at an arbitrary position in the radiation zone. So we get the gravitational field in the radiation zone. And then we do the integral over the radiation zone to find the contribution from the radiation zone of the gravitational of the source. And so we do this integral over of the effective stress energy tensor, and there is no matter in the radiation zone, so T comes 0, and we plug what we find from here in this, and we evaluate that at the observer position. And then we get the prediction for, so then we get the gravitational field, like the gravitational wave that we receive at the detector, if we sum up the near zone calculations and the radiation zone calculations. But these solutions usually depends on like the velocity of both black holes, on the two masses, also on the acceleration of the black holes. And we would like to reduce the number of parameters we describe the system. And we use what is called the relative parameters. And so we're using the center of mass frame. So instead of talking about the position of each black hole, we talk about the relative position, the relative velocity, and the two masses. This we cannot do anything with it. And also to replace the acceleration that we find in the gravitational waveform in the solution, we use the two-body equation of motion. So because we know the metric, or like the gravitational field in the near zone, we can calculate using the geodesic equation. You can calculate the acceleration of the two black holes. So you have here, for example, the Newtonian force, and then you have post-Newtonian effect from gravity, from general relativity that comes into play. And you can put that in the gravitational waveform to find a simpler version. So the solution looks like this. So the solution, so you add up the near zone and the radiation zone contribution, make the change of variable, and you get something of this form. So you have mu is the reduced mass, m1 times m2 divided by the sum of the mass. And you have a factor 1 over r. It makes sense because we neglected terms that decay faster than 1 over r. So the solution only decays as 1 over r. And here you have the polarization, or like the waveform of the gravitational wave. That depends on the relative velocity, the sum of the mass, and the distance between the two black holes. And this is what is called the quadrupole formula in general relativity. And this is the leading contribution that we find. I don't write the higher contribution. They're lengthy and a bit complicated. But it is conventional to call those higher order and to increment each order by 0.5 instead of 1. So next to leading order would be the order 0.5, then order 1, 1.5, etc. All right, so now how do we add the scalar field to this problem? So as we said, we would like to describe horn density theories
that have luminal propagation of gravitational wave, and theories that have screening mechanism. So to do this, we write the action in this form. So you again have this non-minimal coupling between the scalar field and gravity. You have a kinetic term, a Bronsted term, usually, if you know about it, where you have omega is an arbitrary function of the scalar field. Here you have the kinetic term of the scalar field again. And then you have three different terms representing the three different screening mechanisms. You have the chameleon screening with the potential, kinetic, camouflage screening, and the Weinstein screening. And those function gamma 2 and gamma 3 are arbitrary. Here we added also a little factor delta C, delta K, and delta V, because when we work with a theory, we don't want this theory to have different screening mechanism because we don't really know how to deal with different screening mechanism at the same time. So typically, if you want to work with a theory that has chameleon screening mechanism, you would take delta C equal 1 and the rest equal to 0. And similarly for camouflage, for example. And this parameter alpha is what is called a scaling parameter, and it will tell you how strong is the screening mechanism depending on its value. So how do we find now the equation of motion that we need to solve to find the gravitational field? So at long range, we make the assumption that we recover Bronsted theory. So it means that we would have the screening mechanism terms here to be 0 or to not affect the theory at large scale. And this hypothesis makes sense if you think about it with the effective field theory of dark energy. In this theory, you can show that screening mechanism at cosmological scales does not impact the cosmological behavior of the theory. So it makes sense to neglect them when you do the calculation. And so, which is nice is that in the case of Bronsted, so if you only consider those two first terms, you can also find wave equation for the gravitational field and the scalar field by using this changer variable. So we have just a scalar field here in the expression of the gravitational field. So the wave equation for the gravitational field would look like this, where you have the same effective stress energy tensor than in general relativity. And you have an extra term that include the gravitational field and the scalar field inside. And the scalar field also have a wave equation. So with an effective stress energy tensor that depends on matter, the gravitational field, and the scalar field itself also. In the near zone, we use what is called the scaling method to find the effective field equation. So because we have screening mechanisms, so it's usually complicated to take the theory itself and make a post-Internal approximation of this. We don't get the proper prediction. So we need to first find effective equations that describe the behavior of the scalar field and the correction to the gravitational field. So how it's done, usually you take the scalar field around its background value phi 0, and you add a small contribution alpha, so the same alpha as up to the power of q, and q is a number that is uniquely defined for each screening mechanism. We'll see just after a bit how that works. And using this approximation, we can find also an equation for, so you have the metric would be then described by general relativity plus a small correction, and we just need to find the equation for the correction and the equation for this scalar field. So because the scaling method is really what we used to calculate this extra contribution for the scalar field, it's important that we introduce it maybe a bit better. So I will show you how to find those equations using the scaling method in the context of the cubic Galilean example. So we have a Weinstein screening mechanism here at play. So as I said, the idea is to add to now approximate the scalar field being close to its background value phi 0 and add a small contribution. And here we assume this alpha to the power of q to be smaller than 1, to be very small. And for now, q, we keep it to be arbitrary. So you get a solution would be an action like this. And here you see that you recover general relativity and extra terms that depend on the scalar field. Now,
if you take alpha to the power of q tends to 0, except if we choose a specific value for q such that this term would not tend to 0. In the case where we take alpha to the power of q tends to 0, we would recover general relativity, right? If we take this limit, except in special case for q, we would recover general relativity. And so at leading contribution, this approximation leads to general relativity. And that's what we want because we're in the screening region. And to find the equation of motion for this contribution psi and the extra contribution of the metric, we can take the next to leading order. And for this, if we come back a minute above, we see that if we consider alpha to the power q to be a small parameter and we do an expansion around it, the leading contribution would be at the order alpha q to the power of q. And so this term is at the order alpha q to the squared, so it's negligible compared to this one. And so we're left with those two terms. Now, if we choose q such that those two terms does not have the same order, it would lead to inconsistencies. Typically, if this term would be the leading contribution, we would take the equation of motion for this Scalar field psi would be a constraint. It would be r equal to 0. And this is similar to say that the energy momentum tensor is 0. And in the case typically of gravitational wave from a source that is non-zero, we cannot assume the energy momentum to be 0. So we need to choose q such that this term and this term have the same order. And this is uniquely defining q. If we choose q equal -1/2, this power and this power are the same. And so we get an action of this form where they have the same order. And if we take the Euler-Lagrange equation, then we get the metric, the equation for the metric or the correction, and the equation for the scalar field psi. This method looks a bit special, but it's been shown to be equivalent or really to represent screening mechanism in the screening mechanism we use, typically the chameleon, camouflage, and Bernstein screening mechanism. So it's really giving the good equation. All right, so now let's go to calculate the effect of the scalar field. So we will first look at the screen region here. So you have the scalar field psi. So this small contribution that we saw we can find using the scaling method. And we first look at what is its effect on the behavior of the source. So since we can find the equation of motion for the metric and the equation of motion for psi, we can find the post-Newtonian approximation in this case. So as we saw, it should look like you recover general relativity and you have an extra correction that is attenuated by this factor alpha to the power q, which is assumed to be small. And at Newtonian order, so at leading contribution, we have here alpha q to the psi, and then we have some post-Newtonian corrections that are a bit complicated, so I don't write it here. Similarly for the OI component and the IJ component. Now we know the metric and the correction to the metric in the near zone, so we can calculate the equation of motion with the geodesic equation. So we get that the acceleration, we still have a Newtonian term from general relativity, and we have this correction term that enters at the same order as the Newtonian term because of this contribution that is at leading order in the metric. The only difference is that you have this factor alpha to the power q that attenuates, and this term then will end up to be smaller than this contribution. And then you can calculate, so you have the post-Newtonian correction from general relativity and the correction from the scalar field here, again attenuated by this factor alpha to the power q. All right, if you take now this acceleration and put it in the gravitational waveform that we calculated using general relativity, you find the contribution, or this contribution from the fact that the source is affected. So you get an extra term in the gravitational waveform that looks like this. you have mu divided by 2r, so the same factor as we had in the gravitational for gravity or for general relativity. And you have the derivative of the scalar field at position 1 and 2 of the black hole. And this enters at leading order, so at the same quadrupole order as general relativity, but we have this factor alpha to the power q. So depending on how small is this parameter, this whole contribution will be more or less small compared to general relativity. So what about the second contribution from the scalar field to the gravitational wave? So for this, so as I said, we know the gravitational field in the near zone, and we can find the scalar field psi using its equation of motion. I forgot to say, but the equation of motion for psi, I don't write it here. It depends on the screening you're using. The equation will depend, but you have an equation that you can solve, and you solve it for the scalar field, and then you can calculate really what its effect. So what you need to solve is this field, this gravitational, this wave equation. So you need to take the retarded integral of this effective stress energy tensor, and we do this integral over the near zone. So if you do the integral of this term, it would give you general relativity, because a part of the gravitational field is described by general relativity. And then you do the integral over the near zone of still this term, but this time with the correction to the gravitational field. So you have the energy momentum tensor and the correction to the gravitational field. And you should also calculate the effect of this extra effective stress energy tensor. But in this case, we don't need to, because the scalar field and its derivative always appear squared also. And so instead of having a contribution at the order alpha to the power q, you get something at the power alpha q to the square. And so it's negligible compared to this correction. So I actually don't need to calculate the integral of this term. So now if you do the calculation of this extra term, you get something complicated, but that enters at next to leading order compared to the leading order of general relativity. And also attenuated by this factor alpha to the power q. So we expect this contribution to be smaller than the one we just saw, because it appears at lower order. And finally, maybe the most promising contribution from the scalar field, because we expect this to be unscreened. We need to know the scalar field in the radiation zone, and then calculate its retarded integral. So this time, we actually don't need to consider any extra contribution to the general relativity metric or the scalar field, because they will enter at a lower order. I mean, you can add them, but as we will see, we actually can just consider our source to be fully screened. So there's no dynamical scalar field, and we recover general relativity in the near zone. So what we want to do now is to solve the wave equation in the radiation zone. So for that, we need the scalar field in the radiation zone. And since the scalar field is itself sourced by matter, that's why we don't need to have a contribution of the scalar field in the near zone, because the radiation zone scalar field is sourced by matter and the gravitational field in the near zone. So we can just take the retarded integral of this to find the scalar field in the radiation zone. And then we can take the retarded integral of this in the radiation zone as well. So we recover general relativity as always from this an effective stress energy tensor. But this time we need to integrate this one, the second one, where we plug in the gravitational field in the radiation zone, the same as general relativity, and what we found for this radiation zone scalar field. And if we do the calculation, we get something of this form. Again, always we have this factor mu divided by r. Here we have the parameter omega 0 is this function omega phi evaluated at phi 0. And then we have the waveform depending on the velocities and the position of the object.
And this you can show it's at 1.5 order compared to general relativity, but it doesn't have this factor alpha to the power q that make this term smaller. So even though it enters at lower order than the one we calculated before, it's not for sure that this contribution would be smaller than the one before. So to finish on this presentation, I will show you a case study, so the cubic Galilean model that we saw before, and try to see if those contributions are visible or not. So we have this cubic Galilean theory like this, and to satisfy cosmological observation, it's usually accepted that we would need to have this parameter omega 0 here that is constant to be roughly 10. This alpha to the power q to be roughly equivalent to the Hubble constant, and the q, as we saw, it was equal to -1/2. So what we want to know now is, so this term, so that's the extra contribution from the long range effect of the scalar field on the gravitational field compared to general relativity. It looks something like this, where you have this parameter omega 0, and it will depend on the mass and the distance between the two black holes. And here you have the effect of the scalar field on the source as compared to the gravity GR, and we see that we have this parameter alpha to the power q in front of it. And in practice, if we take data that or predicted data, we would have that typically for the first gravitational wave that we ever observed in 2015, the term from the long range effect that appears at 1.5 in the post-Internal Approximation, it would be, so the amplitude of this term would be at the percent level than the term in general relativity, and the effect on the source, because this alpha to the power q is so small, would be actually completely unobservable compared to general relativity at 10 to the -20. Now, if we take two supermassive black holes, this effect would be amplified slightly, but still completely unobservable. And similarly for asymmetric black hole, if we take a stellar mass black hole with a supermassive black hole, we would improve it a bit, but it's still out of reach, or even hoping to ever observe this effect. So nowadays, our detectors have on the amplitude, the effect on the amplitude of the sensitivity on the amplitude is at the order of 10 to 20%, I think. It's not very precise. So for today's observation, we can conclude that the effect is negligible, but it might not be the case for a future detector. So just to conclude now, so we calculated the leading effect of screening scalar field on the gravitational wave, and we find that there were 3 different effects that we can expect, and these effects are negligible for today's detector. But the future detector like LISA and the Einstein telescope are expected to have a sensitivity on the amplitude of the gravitational wave at the percent level. So at the same level as the long range effect of the scalar field. So we could observe, we might be able to observe the effect of the scalar field there. And also something interesting is that because of the frequency range of LISA, it would be possible to observe a stellar mass black hole merger a decade or 2 before the actual merger. So while we observe it with LISA, we could make a prediction on when do we expect the merger to happen. And then there is a frequency gap where LISA is not able to observe the system, and the Einstein telescope neither. And if we make a prediction, typically using LISA observation on when the merger happened, and we can then test with the Einstein telescope if the prediction was right, if compared to general relativity, for example, or if there was a discrepancy that could be then caused by the fact that the source was not behaving as it used to be, or because there was scalar wave that was emitted, and so the source was decaying faster or less fast. And so that could be an idea to observe an effect of the scalar field, even if this effect is small, because it's accumulated over 10 years, maybe on the source, it might be observable. And for future work, something that would be really interesting to look at is the effect, the scalar wave that is emitted, because like we calculate the scalar field in the radiation zone and its effect on the gravitational field, but we didn't calculate the effect of the scalar wave on the detector. And that might be non-negligible, because as we saw, the scalar field is not screened at long range, but usually it's assumed that Earth is in a screened environment, and so the scalar field has only a little effect on the detector. But something that could be interesting is that scalar wave, they affect the amplitude of the wave, but they also affect the polarization. And our detectors might be more sensitive to the polarization than the amplitude. And so even if this effect is small, it might be observable. And something else that we can do that we didn't look at is the energy loss due to this extra scalar field. And then we could compare typically the data with pulsar timing or the solar system where we calculated the energy loss due to gravitational wave with great precision. And we observed it with great precision as well. So we might be able to also see a discrepancy there, or to constrain those theories. Thank you.
Excellent.